Volt amps, abbreviated VA, and kilovolt amps, abbreviated kVA, are used to rate electrical equipment because they represent the apparent power, which is the total power a device seems to be using. This is different from watts, which represent the real power, the actual power used to perform work. The difference between apparent power and real power is due to the power factor, which is the ratio of real power to apparent power. Inductive loads, like motors and transformers, cause the current to lag behind the voltage, creating a power factor less than 1.0. This means the device is drawing more current and is actually being used to do work. Using VA or kVA gives a more accurate picture of the total electrical load on a system. Many devices, like motors and transformers, can be wired for different voltage and current configurations. For example, a motor might be wired for 240 volts or 480 volts. The kVA rating remains constant regardless of the voltage. This simplifies load calculations because you don't have to recalculate the power rating for each voltage option. The formula to find volt amps is voltage multiplied by amperage. To find watts, it is voltage multiplied by amperage multiplied by the power factor. Let's consider a motor with a kVA rating of 10 kVA. This motor can handle a maximum apparent power of 10 kVA, regardless of the voltage at which it operates. If the motor operates at 240 volts, and to reach 10 kVA it requires 41.67 amps, the apparent power will be 10 kVA. If the motor operates at 120 volts and draws 83.33 amps, the apparent power remains 10 kVA. If you only use voltage and current ratings, you'd have to specify both values, making comparisons and calculations more complex. kVA ratings provide a single value representing the maximum power the device can handle, simplifying comparisons and application suitability assessments. Here's why this is important for load calculations. Firstly, consistent rating. kVA provides a consistent measure of the equipment's capacity, regardless of the operating voltage. This is crucial for electrical system design and ensuring the equipment operates within its safe limits. Secondly, simplify sizing. Using kVA simplifies the process of sizing circuit breakers, transformers, and conductors. Electrical engineers and technicians can use the kVA rating to determine the appropriate size of these components. Thirdly, accounts for reactive power. kVA includes both real power measured in kilowatts and reactive power measured in kilovolt amps reactive. This is important for understanding the overall load on the electrical system, especially when dealing with inductive loads. Consider a transformer. A transformer is rated in kVA because its capacity is limited by heating, which is related to the current flowing through its windings. The current is determined by the apparent power, not just the real power. Therefore, the kVA rating is a more accurate representation of the transformer's capacity. For example, a 25 kVA transformer can supply 25 kVA of apparent power. The amount of real power in kilowatts that it can supply depends on the power factor of the load. If the load has a power factor of 0.8, then the transformer can supply 20 kilowatts of real power. The remaining 5 kVA is reactive power, which circulates in the system and does not perform any useful work. When performing load calculations, firstly determine the kVA of each load. This information is typically found on the equipment's nameplate. Secondly, add up the kVA of all the loads in the circuit. This will give you the total kVA load in the circuit. Thirdly, select a circuit breaker, transformer, and conductors that are large enough to handle the total kVA load. Make sure that the equipment is rated for the voltage and current of the circuit. Understanding the relationship between kVA, voltage, current, and power factor is essential for electrical professionals. It allows them to design and maintain electrical systems that are safe, efficient, and reliable. In summary, VA and kVA ratings are preferred over solely voltage and current ratings because they firstly simplify load calculations by providing a single value that represents the total apparent power. Secondly, accommodate devices that can operate at multiple voltages and currents without requiring recalculations. Thirdly, provide a more complete picture of the electrical load on a system, accounting for both real and reactive power. Remember that apparent power, measured in volt amps or kilovolt amps, is the product of voltage and current. Real power, measured in watts or kilowatts, is the power actually used to perform work. The power factor is the ratio between real power and apparent power, reflecting the efficiency of power usage. For instance, a motor operating at 480 volts and drawing 20 amps has an apparent power of 9,600 volt amps or 9.6 kVA. If the motor's power factor is 0.8, its real power is 7,680 watts or 7.68 kilowatts. When selecting a generator, the kVA rating is crucial. If you have several loads with a combined real power requirement of 15 kilowatts and an average power factor of 0.75, the total apparent power is 20 kVA. Therefore, you would need a generator with a kVA rating of at least 20 kVA. Sizing conductors requires consideration of the ampacity, which is the current carrying capacity of the conductor. The kVA rating helps determine the appropriate conductor size. For example, a 10 kVA load at 240 volts draws approximately 41.67 amps. You would need to select a conductor with an ampacity greater than 41.67 amps, taking into account any dating factors for ambient temperature or conduit fill. When selecting a transformer for a building, you need to consider the total kVA load of all the equipment in the building. This includes lighting, HVAC systems, appliances, and any other electrical loads. By calculating the total kVA load, you can select a transformer with an appropriate kVA rating to meet the building's power needs. Circuit breakers and fuses protect electrical circuits from overcurrents. The kVA rating helps determine the appropriate size of these protective devices. For example, a 5 kVA load at 120 volts draws approximately 41.67 amps. You would need to select a circuit breaker or fuse with a rating slightly higher than 41.67 amps, such as a 50 amp breaker, to provide adequate protection. In commercial buildings, large motors and HVAC systems contribute significantly to the overall kVA load. Accurately calculating the kVA load of these systems is essential for proper electrical system design. For example, a large HVAC unit might have a kVA rating of 30 kVA. This kVA rating needs to be included in the total load calculation for the building. Power factor correction can improve the efficiency of an electrical system. By adding capacitors to the system, the power factor can be increased, reducing the amount of reactive power and lowering the overall kVA demand. This can result in lower energy bills and improved system performance. Understanding the different wiring configurations of devices, such as single-phase or three-phase, is important for accurate kVA calculations. Single-phase devices typically have a voltage rating of 120 volts or 240 volts, while three-phase devices typically have a voltage rating of 208 volts, 277 volts, or 480 volts. The kVA calculation will vary depending on the wiring configuration. Using kVA ratings simplifies the process of comparing different devices. For example, if you are choosing between two different motors for a particular application, you can compare their kVA ratings to determine which motor is most suitable. The motor with the lower kVA rating will typically be more energy efficient. The National Electrical Code, or NEC, provides guidelines for electrical installations, including requirements for conductor sizing, overcurrent protection, and equipment ratings. The NEC uses kVA ratings as a basis for many of its requirements. Therefore, it is important to understand kVA ratings to comply with the NEC. When performing electrical work, always follow safe work practices. This includes wearing appropriate personal protective equipment, de-energizing circuits before working on them, and following lockout-tagout procedures. Working with electricity can be dangerous, so it is important to take precautions to protect yourself and others. The kVA rating is crucial for generator sizing, ensuring it can handle the total apparent power demand. Conductor sizing relies on kVA to determine the appropriate ampacity for safe current carrying capacity. Transformers are selected based on the building's calculated kVA load, accommodating lighting, HVAC, and appliances. Circuit breakers and fuses are chosen using kVA to provide overcurrent protection, preventing damage from excessive amperage. Large motors and HVAC systems, common in commercial buildings, significantly impact the overall kVA load, requiring precise calculations. Power factor correction improves system efficiency by reducing reactive power, thereby lowering kVA demand. Single-phase and three-phase wiring configurations affect kVA calculations, necessitating accurate voltage and current considerations. Comparing different devices by their kVA ratings aids in selecting energy-efficient options for specific applications. Adherence to the National Electrical Code, which uses kVA for various requirements, is essential for safe and compliant installations. Always prioritize safety, using personal protective equipment and following lockout-tagout procedures when working with electrical systems. Understanding kVA and its implications is crucial for electrical engineers, technicians, and anyone involved in electrical system design, installation, and maintenance. It ensures efficient power usage, safety, and compliance with electrical codes. Consider a panel board with multiple circuits. Each circuit has a specific load in kVA. To determine the total load on the panel board, you must sum the kVA of all the individual circuits. This total kVA load is used to select the appropriate size of the main circuit breaker for the panel board. In industrial settings, machinery often has high kVA demands. These machines may include motors, welders, and other heavy equipment. Accurately assessing the kVA load of these machines is critical for designing a reliable electrical system. For renewable energy systems such as solar photovoltaic systems, the kVA rating of the inverter is an important factor. The inverter converts direct current electricity from the solar panels into alternating current electricity for use in the building. The kVA rating of the inverter must be sufficient to handle the total load of the building. The power factor is a critical aspect of kVA calculations. Improving the power factor reduces the amount of reactive power, leading to a more efficient and cost-effective electrical system. Power companies often penalize customers with low power factors. Proper grounding is essential for electrical safety. The grounding system provides a path for fault currents to flow back to the source, tripping circuit breakers and preventing electrical shock hazards. The grounding system must be properly sized to handle the available fault current, which is related to the kVA rating of the electrical system. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes or other electrical disturbances. The kVA rating of the electrical system is a factor in selecting the appropriate SPD. Harmonic distortion can also affect kVA calculations. Harmonics are caused by nonlinear loads, such as electronic devices and variable frequency drives. Harmonics can increase the apparent power and reduce the power factor. Electrical codes and standards provide guidance on how to address harmonic distortion. In healthcare facilities, a reliable electrical system is critical for patient safety. The kVA capacity of the electrical system must be sufficient to support all of the critical medical equipment. Backup power systems, such as generators and uninterruptible power supplies, are often used to ensure that critical loads remain powered during power outages. Regular maintenance of electrical equipment is essential for ensuring reliable operation. This includes inspecting and testing circuit breakers, transformers, and other electrical components. Proper labeling of electrical equipment is important for safety and efficient troubleshooting. Labels should clearly indicate the voltage, current, and kVA ratings of the equipment. When working with electrical systems, it is essential to have a thorough understanding of electrical theory. This includes knowledge of voltage, current, resistance, power, and power factor. It's important to remember that safety should always be the top priority when working with electricity. Always follow safe work practices and consult with a qualified electrician if you have any questions or concerns. Understanding the concepts of kVA, voltage, and current is an important tool in ensuring a safe and efficient electrical system.